So we'll continue our discussion of four-way mixing. Right. So you were discussing this process, right? Where we have a strong pump wave at omega p, which is interacting with two weak waves, signal and idler, right?
So marker is low, so darkness.
Sorry?
So marker is very light, sir.
It's very light.
I don't know. Maybe.
Can you see this?
Yeah.
This is too much in the corner. So is that visible?
Yes, sir.
Yeah, so we're discussing this four-way mixing process, right? So we had a strong pump wave at omega p, and then weak waves called signal and idler, right? Of course, the frequencies are related like that, and so if you consider some waveguide or fiber or something, and all these fields are so AP pump signal idler are co-propagating along this waveguide, and Z is the propagation direction, right? And we took the electric fields to have some transverse mode profile. So this could be pump signal or idler, and typically we took all of them to be the same in the same mode, right? Okay, so we took the electric field like this. So I mean, if you have to be really consistent, then I have to add a complex conjugate, right? And then we sort of started from the coupled propagation equation. We wrote down the third order nonlinear polarizations, and then wrote down different terms which will arise, right, in the coupled amplitude equations for the three waves, pump, signal, and idler. And we got so far as, so we got some general solution for the signal and idler, right? So if you remember, last time we got solution like this. Right, and this B was related to the original amplitude A, just with a phase factor, right? So this B was just A times this phase factor minus 2 gamma P. Right. So we can also write the solution for the original amplitude. Right, we just multiply this by the phase. And if you remember, this delta beta total was sort of the bare delta beta minus this nonlinear shift, right? Where delta beta was sort of the difference in the propagation constant. Right, so A also has the same solution, just the phase is a bit different. Right, so here delta beta prime is okay. Similarly, you can see the idler also has the same form. Okay, and then recall this G, the gain factor G. So dependent on the pump power and this total phase mismatch, like that. Right, so today we'll see how this can be used for parametric amplification. And wavelength conversion. So basically, we need to find these constants CS1, CS2, CI1, CI2 using boundary conditions. Right. So we know our input fields, right? So at z equal to 0, we are sending in some field amplitudes depending on the power of the waves, right? So, for example, so the input signal amplitude is, so at z equal to 0 with CS1 plus CS2. Right, so that's one boundary condition. The second boundary condition, so we also had a so remember we had an equation for dA by dz. So dAs by dz. So we can put z equal to 0 for that, right? And this was equal to, we had on the right hand side two terms. So first term was the cross phase modulation from the pump. So basically we put z equal to 0 in that equation. So As at 0. And then we had this four-way mixing term, which had AI conjugate for As, right? So that also we put z equal to 0. So that will give us the second. So we have four unknowns basically, right? So we need four boundary conditions. So we'll get two boundary conditions from the signal equations and then two boundary conditions from the idler equation. Right? So these two are from the signal. Right? And dAs by dz at z equal to 0 we can compute from the solution for As. right? So on the left hand side, we can compute dAs by dz at z equal to 0 from here. So if you just do that, and again, then AS0 we can substitute CS1 plus CS2. Actually, I think leave this as AS0 because we want to find a solution in terms of AS0 and AI0, right? Those are our input fields. Right, so we can simplify this equation a little bit. To simplify this equation, just collect terms. You get okay. So I've just written delta beta prime in terms of delta beta total. Right, so delta beta prime is delta beta total plus 4 gamma p. Okay. Basically, if you do that, then you get delta beta total here. Okay, so basically now we have two equations here in CS1 and CS2. So basically, we can solve for the constant CS1 and CS2 in terms of the input field amplitudes AF0 and AI0. Okay, so if we go ahead and solve, so it will be good idea to go through each step on your own at home. Just solve it on your own and check that you get what I'm saying. Right. So then the solutions are okay. So you can check CS1 plus CS2 will give you AS0 because this term will cancel and this term will cancel. Okay, and then basically now we plug in CS1 and CS2 into the solution for AS. So which was CS1 times e to the gz plus CS2 times e to the minus gz. So I can write the solution for the signal field. So just to rewrite the solution, and we put CS1 and CS2, so you get okay. So I basically collected terms with AS0 and AI0. So yeah, just plug in CS1 and CS2 these into here. Right, so we get terms like e to the gz plus e to the minus gz by 2. What function is this?
Cos. No, I know.
Yeah, so this is a hyperbolic function, right?
Okay.
So, I mean, if you add I here, then it will be cosine, but
Yes, sir.
so these are exponential functions. So this is cosine hyperbolic of gz, and then e to the gz minus e to the minus gz is sine hyperbolic. Similarly, here this is sine hyperbolic. Okay, so then we have the solution for the signal wave. So we get in terms of hyperbolic functions. And the signal amplitude at any position z depends on the input signal amplitude and also on the input idler amplitude. right? Similarly, you can check for yourselves. The idler wave solution can also be written in a very similar manner. Basically, you just flip the roles of S and I. Okay, so given any input condition, right? We know the solutions for the signal and idler waves, right? So the input signal and idler amplitudes, of course, figured here. Also, the input pump power figures in gamma. With gamma. Right? So typically, the configuration which is most used for this application, right, parametric amplification or wavelength conversion, is typically we launch only one of these weak fields, either signal or idler. So usually the field we call, which we launch at the input, we call signal, and we basically say there is no idler launched at the input. Okay, so in most applications, typically there is no idler wave at the input. Okay. So then, in this condition, we can find out what is the power in the signal wave after, let's say, propagating a length L in my device. So output signal power. P is just the mod square of A, yes, because remember we started by normalizing the fields such that mod square of the amplitude gives me power. Right, so basically in this solution I put Z equal to L and AI equal to Z, AI at 0 equal to 0. So this term goes away. Right, and I take, so just this first term remains, and I take mod square of that. Okay, so mod square, so this is some real part plus imaginary part, so mod square is this square plus this square, right? So mod A is 0 square is just the input signal power, right? So the signal power launched at the input. So basically you can see this multiplication factor is the gain for the signal, right? That's output signal power by input signal power is this. Right, so one thing to erase that, but one thing to note from the solutions was you saw that the signal amplitude was dependent on the input signal and also the input idler amplitude with the conjugate, etc. Right. So basically, this, like any other parametric nonlinear process, is a phase sensitive process. So it depends quite sensitively on what my input amplitudes are and what my in the sense what intensities are sent in, and also what phase they are, right? So because that AI came as AI conjugate, so it's important what the signal and idler phases are also. Okay, so in a slightly different configuration, for example, you can build what are called phase sensitive amplifiers, which amplifies only certain phases. Okay, so if you send in an input wave which has a particular phase, then it will get amplified. But if you send in, if the phase is, let's say, pi out of that phase plus pi or something, then it will get attenuated. Okay, so that's called phase sensitive amplification. So any parametric nonlinear process depends on the phases of the fields involved also. It's the coherent process basically. Right. So coming back to this,
Sir,
yeah.
sir, I have a question. In the normal crystal, we can launch the pump to conjugate pumps beams in the opposite direction. But here, how can we achieve that in the inside the fiber?
Sorry, I didn't understand. What do you mean? Launch
So
to?
actually, for to generate for four-way mixing, we have to generate two. Sorry, we have to put two pump beams in the opposite direction. So, but in the
No, no,
fiber, how
so
can?
here it's here. It's just in the same direction,
Okay, we
right?
are
So
taking.
all the pump signal either are co-propagating, and
Okay,
both these pump photons come from the same beam.
okay, sir.
Okay, so
Okay,
we actually have only one pump beam. We don't have two pump beams, right?
okay, okay, sir.
In the generate case.
Okay, sir.
So in actuality, physically, you are only sending three fields, but there are only three fields interacting in the wavelet. Although it's called four-way mixing, right? So in the general case, okay, you can have these two different, in which case you can send in two different pumps with two different frequencies, right? But yeah, again, you can have them co-propagating, for example. So you can set it up how you want, right? So for example, we can also consider the case that you are suggesting. Okay, let's say you have two pumps, one, and they're counter-propagating. Sort of something like we had in the optical phase conjugation case. Right, so fine, you can write down the equations for that, right? You can start from the coupled amplitude equations. So some signs will get flipped, and basically you can see your solutions will be different. Okay, so your phase matching conditions will be different, and your final solutions will be different.
Okay, sir.
Okay, but like if you want to do amplification, like if you want to build an optical amplifier which is efficient or do wavelength conversion, then typically the co-propagating case is much more efficient than with counter-propagating pumps, for example. Okay, and that the main reason for that is basically phase matching. So we saw that this delta beta total has to be close to zero, right, for the process to be efficient, for this G to have a large real value. So that's easier to do when they're all co-propagating. When they're counter-propagating, it's it's very difficult or almost impossible to do, right? Because the k vectors now add in the opposite direction, right? So but it will be good exercise, for example, if you just consider the case, write down the equation and see how it's different from this case. Okay. So here, then the output signal power by input signal power is some gain, right? So, or signal gain. And that's given by this expression. So we can simplify this a little bit more. So you can use the relation cosine hyperbolic square is 1 plus sine hyperbolic square. Okay, and then just get an expression in just in terms of sine hyperbolic. Okay, so that's the expression for the gain. You can also simplify it a little bit more and write it in a slightly different, or write it in even simpler form. So we know this G the expression for G is that, right? G square is that. So basically, if you get this to the other side, it's G square plus delta beta square by 4. Right? Or if I divide by G square on both sides, right? So this 1 plus delta beta square by 4G square is the expression coming here, but you can see that's just equal to gamma p by G. Right? So I can replace this whole thing just by gamma p by G. So then the gain for the signal okay. So the gain for the signal is of course 1 plus some number, which means it's always more than 1. So this is of course in the absence of any losses, right? We are not taking any propagation loss or anything. So in that case, so when the pump power is 0, the gain is 1, which means the signal the output signal is the same as the input signal. But when we send in a finite amount of pump power, we see that the signal acquires amplification and the output power is more than the input power. And the gain scales very non-linearly, right? So of course there is a p square here, but also G has pump power, right? So it scales in a very non-linear manner. Similarly, we can calculate the output idler power. Right, so we have expression for AI also. So from that we can calculate Pi, the idler power. So at the output at Z equal to L, the idler power will be again we can calculate like that, right? And then again, if you go back to your expression for AI, and then just calculate this with the condition that the input idler AI is 0, then you'll see that the output idler power depends on the input signal power, because at the input there is only the signal, there is no idler, right? So, and this factor is called the conversion efficiency. Okay, and you can check, you'll get this same factor. This same gamma p by g squared sine hyperbolic square gl is what you will get here. So just without the 1, right? So basically, in other words, also the signal gain is equal to 1 plus the conversion efficiency. Right? So why is it called conversion efficiency? This is giving me what fraction of my input signal power is converted to idler at the output, right? So that's why it's conversion efficiency. Of course, the conversion efficiency can be more than 1, right? Because I'm looking at the output idler power divided by the input signal power. And signal and idler are both getting amplified as they are propagating through the nonlinear medium. So, of course, this number can be much larger than 1, right? And basically for G much larger than 1, then this conversion efficiency factor is a number much bigger than 1, then and the signal gain is basically the same as conversion efficiency because 1 is small compared to that. Okay, so basically what is happening? I'm sending in a strong pump and a weak signal wave at the input. Due to the four-way mixing interaction at the output, the signal wave is much stronger. It has been amplified. And also in the process, I've generated a wave at a new frequency, right, which we call the idler. Okay. So the signal getting amplified, that's called parametric amplification, right? Sometimes this device is also referred to as an OPA, optical parametric amplifier. Okay, because I mean it's an amplifier because it's amplifying your signal, and it's parametric because the mechanism used for amplification is a parametric nonlinear process. Okay, there are different kinds of OPAs. So this one is based on Chi3 four-way mixing, right? There are other OPAs which are based on, let's say, Chi2 interactions, etc. But basically, the principle is if you can build an optical amplifier using a parametric nonlinear process, that's called an OPA. And then, since you're generating a new field at a different frequency, right? You're converting. So let's say what could happen is, again, let's say you have some in the optical communications context. Let's say you have some data on your signal feed, right? So this is my signal power. It has some data on it, right? And nowadays in optical communication networks, you have this concept of WDM, right? Wavelength division multiplexing, where data on different routes are sent through different wavelengths. So this is at the wavelength lambda s or frequency omega s. So let's say I want to transfer this data to a different wavelength, lambda I, and then send that to a different part of the network, right? Then I can use basically this four-way mixing process, right? So for example, assume I have a strong pump. So let's say I send in a CW pump, which is strong. And then due to the four-way mixing interaction, what will happen? The signal will get converted to idler, right? And so whenever the signal is there, I'll get some conversion. Right? And I'll basically convert this data onto a different wavelength. That's called wavelength conversion.
Sir, is there a difference between Chi2 and Chi3 based on the optical parametric amplifier and the phase? Either they are phase matched or not insensitive to phase?
Yeah, I mean they're very different, right? So the materials used are different. The phase matching criteria would be different. The wavelengths involved will be very different, right? In the Chi2 case, like it will be something like you'll have one frequency here, right? So here, as we saw, all the frequencies are close together. So omega p, omega s, omega I, right? But in the chi2 case, you'll have something like omega p is equal to omega s plus omega I, right? It will be 3-wave mixing instead of 4-wave mixing. And so you can see that these waves will be at half the frequency of my pump, right? So they'll be much further away from the pump.
Sir, what I've studied last semester was that in the non-degenerate case, the OP is phase insensitive. So here the optical parametric amplifier is phase sensitive. So from where
Yeah.
this
No, so in this case, when I don't have an input, so so this is the case we are discussing for no input idler, right? So when I have no input idler, then of course you can see that the gain is independent of my signal phase, right? So like it just depends on mod of AS. I could have any phase here, but that wouldn't change my gain or conversion. So in that sense, it's phase insensitive, right? In this setup, when I'm not sending any idler, my input signal phase could be whatever, doesn't matter, right? So the gain and the conversion efficiency don't depend on the signal phase. So that way it's a phase insensitive amplifier. But if I'm sending both signal and idler, then the phase or the phase difference between the signal and idler is important. You can check from those equations, the AS and AI. Actually, yeah. So one case where it's very evident is, let's look at the opposite case. So here we have pump degenerate, and then signal idler different frequencies, but you could have the opposite case. So I could have non-degenerate pumps, so omega p1, omega p2, and then a degenerate signal and idler. So omega s, omega s, omega s is equal to omega I. Okay, so in this case, you will see that explicitly, like the gain, etc., will depend on the phase of AS, right? Because basically, in those solutions, AS and AI are the same, right? So AS depends on AS and AS conjugate, right? AS at a particular distance depends on the input AS and AS conjugate. So in some sense, it's depending on the phase at the input. So this would be a phase sensitive amplifier.
Sir, can you explain the case of phase sensitive amplifier again?
So did you understand? So this one,
Yes, sir.
what we mean by phase insensitive amplifier, right?
So it doesn't depend.
When we don't send the idler, then the gain of the signal doesn't depend on the input phase of the signal.
Okay, sir.
Right? That's what we are saying by phase insensitive amplifier. But in this case also, if I send both signal and idler at the input, then the gain and conversion efficiency will actually depend on the relative phase of signal and idler. Okay. Right? Of course, it's straightforward from the equations you can check. Right? So any parametric nonlinear process is phase sensitive in the sense it depends on the relative phases of the fields involved. But in this case, for the special case of where we are not sending an idler, it's independent of the signal phase. So in that sense, it's acting as a phase insensitive amplifier. To make the phase dependence more manifest, what we can do is consider a slightly different process, right? So instead of a degenerate pump and non-degenerate signal and idler, I'm saying if you consider a non-degenerate pump but degenerate signal and idler. Okay, so you have two strong waves here, pumps at omega p1, omega p2, and the weak beam you want to amplify is at omega s. Okay, So basically, it's a similar analysis, except you just have one wave, right? So in those equations, it's something like AI is also AS, right? So we got AS at Z equal to something times AS at 0 plus something times AI conjugate at 0, right? So in this case, what that would mean is AS at Z is something times AS at 0 plus something times AS conjugate at 0, right? So it means that the amplification or the amplitude after propagating through the nonlinear medium depends on the input amplitude and its conjugate. Or in other words, it actually depends on the phase of the input field. So there you can see it directly is what I'm saying. I mean, in this case also, in some sense it's phase sensitive, but you need to input both waves, like both these frequencies. Then it's sensitive to the phase difference between the two inputs. But in this case, since you have only one input here, it will be directly just dependent on the phase. Is that clear?
Yes, sir.
Okay. So this is a feature which is, I guess, special for parametric amplifiers based on nonlinear optics, right? So you have other types of optical amplifiers, right? So you might have heard of like EDFA, erbium doped fiber amplifier, SOA, semiconductor optical amplifier. So these kinds of amplifiers are not based on nonlinear optics. They're sort of based on some gain medium where you pump atoms to a higher energy level and then you get stimulated emission and amplification due to that. And these processes are phase insensitive. Okay, so these amplifiers are truly phase insensitive. It doesn't matter what my phase of the input waves are which need to be amplified. Whereas for parametric nonlinear processes based amplifiers, the phase is important because basically this is a coherent process. But under certain regimes, right, in certain special cases, you can operate it as if it's a phase insensitive amplifier. Okay. Right. So we can look at some limits of this expression to get an idea of like sort of the magnitude of the terms involved there. Okay. Okay, so first limit we can consider is when this factor G times L. So G is this parametric gain factor and L is the length of the medium. So let's say if this product is much smaller than 1, so it's a very small value. Right? In some sense, you can think of it as this factor gamma p times L, which is, so this gamma PL is the nonlinear phase shift, right? Remember? So if that phase shift is much smaller than 1, right? So in the small gain limit, so either the pump power is small or the length of the medium is small or both are small. Right? So basically the sine hyperbolic of x for small values of the argument, we can just approximate it as x. right? So the first term in the Taylor expansion is just x. Similar to like sine of x for small values of x is x. Similarly, sine hyperbolic of x for small values of x is x. So okay, so that means the conversion efficiency. So I get g square l square from here, and then that g square cancels from here. So I just get gamma p l squared, right? And this gamma p l is basically again the nonlinear phase shift, right? So for small values of the gains or small pump powers, basically the conversion efficiency is just the square of the nonlinear phase shift. Okay, so it grows quadratically with the pump power. It goes as p square. Okay. You can look at a different limit of large phase mismatch. So basically, what we are saying is this delta beta, the phase mismatch, is much bigger than the nonlinear contribution. So remember, we had delta beta total equal to this delta beta minus 2 gamma p. So let's say this delta beta, which is just the difference of the wave vectors, which depends on the dispersion of the medium, right? Depends on the refractive indices at the different wavelengths. Let's say that factor is much bigger than the nonlinear shift. So this means that delta beta total, which is delta beta minus 2 gamma p, I can just approximate as delta beta. Right? And so G was square root of gamma p square minus delta beta by 2 whole square. So again, delta beta total I can replace by delta beta, and then delta beta I'm saying is much bigger than gamma p. So this just becomes square root of minus delta beta square. So if this now G is imaginary. Right. So basically, what we are saying. So remember, we saw how G varies with delta beta, right? And in the range 0 to 4 gamma p, it was real, and beyond that, it was imaginary. So that's what we are seeing. We are seeing delta beta is much bigger than gamma p. So we are like somewhere here or here. So G is basically imaginary. So in some sense, you are not phase matched for the process. So basically, G is this imaginary number which we plug in here. So we get sine hyperbolic of an imaginary number. Right, so the conversion efficiency becomes So sine hyperbolic of iota times some quantity. What is that? So go back to the definition of sine hyperbolic.
Sine of delta beta.
Yeah, so it just becomes sine, right? It becomes a sine function of delta beta by 2. So we get sine delta beta by 2, and then in the denominator we have delta beta by 2 square. So we get sine x by x, which is sinc, right? So it's an L here. Okay, so we get an expression which is sort of this gain gamma PL square times this factor sinc square of delta beta L by 2. So remember we got this sinc square delta KL by 2 in the beginning when we were discussing like some chi3 process, right? And we saw that in the small conversion limit, we get this sinc square dependence on the phase mismatch. So basically we get the same thing. We get sinc square of the delta beta L by 2. Okay, so for large phase mismatch, we recover sort of this sinc square expression that we expect for any nonlinear process in the small conversion limit. Okay, and then third limit we can look at is sort of when the process is efficient. So we have phase matching, so phase match process, and the pump power is also large. Okay, by phase match process, and we are saying that this delta beta total is close to 0. Okay, so the G is close to its peak, right? So we are somewhere here. And pump power is sufficiently large, so this nonlinear phase shift is of the order of unity or more. Right, so the first case we considered was when the pump power was very small, so this nonlinear phase shift was much smaller than 1. Second case we considered was when the phase mismatch is large. So this case is when both of those shortcomings have been overcome. So we have phase matching and we have sufficient pump power. Okay, so then in this limit, you can see G so G is gamma P square minus delta beta total square. And so if you have phase matching, this delta beta total is close to 0. So this G is just gamma P. Okay, so that means this hyperbolic function GL is just sine hyperbolic of gamma PL. Okay, and So if I write it down in terms of the exponential function, gamma PL by 2 minus e to the minus gamma PL by 2 by 2. And now if the pump power is sufficiently large, such that the nonlinear phase shift is of the order of unity or more, then you can see this e to the x term will be much larger than the e to the minus x term, right? So only the positive exponential contributes. Okay, so then my conversion efficiency just becomes the square of that. So we had gamma p over g, right? And so g is just gamma p, so that factor is just unity, and then we have sine hyperbolic square.
Sir,
Yeah.
so this will be possible only when gamma pp of L is very larger than 1, not equal to or comparable to 1.
Yeah, I mean, the larger it is, the better the approximation. But even for, you can see like, I don't know, for 2 or 3 or something, I mean, it's not, but so e to the 1 is whatever, 2.7. E to the minus 1 is 1 over 2.7, right, which is 0.3 or something, right? So it's an order of magnitude already, almost. But yeah, of course, the better approximation as this goes higher. I mean, even if you go to 3 or 4, this will quickly become much larger than this because it's exponential, right?
Okay, sir.
But yeah, these are just order of magnitudes. There's nothing like sacred about one. Right, so it's just square of that. So you can see in this case, basically we get exponential gain or conversion. So it goes exponentially with the pump power. Right, so for small pump powers, we saw that it went as square of the pump power. For large phase mismatch, it also sort of goes as square of the pump power along with this factor of sin square. But if you have phase matching, then it goes exponentially with the pump power. Right? So this is much larger. The scaling, exponential scaling with pump power is much faster than the square scaling. So the process can become really efficient if you get phase matching. Right, so you can see that, I don't know, like gamma PL, if you have four, then gamma PL square is about 16, but e to the 4 is, I don't know, like 80 or something. Right, so with and without phase matching can be quite a big difference. And of course, if you have very low loss in your medium, so optical fibers, for example, you can get really low loss, right? So you can make the length really long, right? So even for decent pump power, you can make the length really long and then make this factor gamma PL large. Okay, so I hope those three limits are clear. Okay. And so for an efficient amplifier, you want to be in this range, right? You want to have phase matching and nonlinear phase shift more than unity, or let's say order of pi or something, more than that. So Another important, I guess, metric for an amplifier is sort of the bandwidth and the frequency range over which it operates, right? So that here depends on basically if I change my omega s, like how does my gain change, right? That's basically. So when I change my frequency, my delta beta changes, right? Because of the dispersion in the medium. So that changes my phase matching and that changes my gain. So let's look at this a little bit more detail. How dispersion affects the phase matching. So the important quantity here is this delta beta total, which was delta beta minus 2 gamma p, right? And this delta beta was 2 beta at the pump minus beta signal minus beta idler. Right, so for phase matching, we want this quantity to be close to 0. So we want this to be close to 0. So basically, we want delta beta to be close to 2 gamma p. Okay, so the frequencies are like this. So omega p is in the center, and then omega s and omega are symmetrically placed. Right, so this, let's say this detailing is delta omega. So omega s plus omega I has to be equal to 2 omega p. Okay, so basically, so this beta, the propagation constant, right? So remember the wave here goes as e to the I beta z. So of course that beta is a function of the frequency, right? So so in general it depends on, for example, the refractive indices of the material which you use to make a fiber waveguide. Plus it depends on the waveguide dimensions itself. Right? So what we do is basically we can do a Taylor. So basically, since these signal and idler frequencies are closely placed about the pump, and we need the propagation constants at these frequencies, we can do a Taylor expansion of this function beta omega about the pump frequency. Okay. So I can write beta of omega as, so beta at the pump frequency plus the first derivative of beta times omega minus omega p plus half second derivative of beta omega minus omega p whole square plus higher order terms. Right? I could include up to any order I want, but for now let's consider up to only second order. Right? So what is beta 1 is d beta by d omega, which is basically 1 over the group velocity. Right? So d omega by d beta or d omega by dk, you might remember, is the group velocity. Right? And then beta 2 is the second derivative of beta with respect to omega, or the derivative of this 1 over group velocity with respect to frequency. Right? So beta 2 is basically a measure of how the group velocity is changing with frequency, right? So that's why this is called GVD, or group velocity dispersion. Okay, so beta 2 is measuring the dispersion in the group velocity, right? So it's a derivative of the group velocity with respect to frequency. So if beta 2 is 0, that means that the group velocity remains constant for different frequencies, right? Which means there is no GVD. So beta 2 is called GVD, and you can see it has units of second square per meter, right? So 1 over velocity, and then this is 1 over frequency, or basically time. Right? So you get second square per meter. The beta 1 is units of second per meter, so 1 over velocity, right? So similarly, higher order dispersion terms, if you want to say, consider the third derivative, beta 3 will have units of second cube per meter, etc. Right? So, and this omega minus omega p, so, okay. So, yeah, so let's consider terms up to second order. And then using this scalar expansion, compute this delta beta, right? So basically for, so beta p will be beta at omega p, which is just beta p. Beta s will be beta at omega s, right? So I'll get omega s minus omega p here, omega s minus omega p here. And beta I similarly will be beta at omega I. Okay? So we plug that in and basically see what so what I'm saying is beta s is beta p plus beta 1 times omega s minus omega p. So I erase that. S omega I, and this is delta omega. Right, so beta 1 times omega s minus omega p is just delta omega. And then the second order term, I'll get delta omega square. For the idler, again, beta p, and then here I'll have beta 1 times omega I minus omega p. So omega I minus omega p is minus delta omega, because omega is less than omega p. So here I'll have minus delta omega, and here I'll have minus delta omega squared. Okay, so then delta beta, which is 2 beta p minus beta s minus beta I can just write from here. So 2 beta p, this beta p will cancel with the 2 beta p. And then this first order term, I'm getting a positive for signal and negative for the idler, so that will also get cancelled. Only term surviving will be second order term. Right, so this will be minus beta 2 times delta omega square. Okay, so the delta beta depends on the detuning, right? So the detuning of the signal and idler from the pump, the delta beta just depends on that, with the proportionality constant being this GVT. Okay, so as I change my signal frequency, automatically, of course, the idler frequency also changes, and due to the change in delta omega, my delta beta changes. Right, so here you can see for a constant GVD, for a constant beta 2, as I increase my detuning, my delta beta will increase, right, as the square of the. So if you wanted to keep higher order terms, then you can see that all the odd order terms will get cancelled, right? Because in one of them you get plus, the other will get minus. So beta 3, for example, you get delta omega cube here, but here you will get minus delta omega cube, so that will get cancelled. But beta 4 term will survive. Right? So if you wanted to consider higher order terms, the even terms will survive. Odd orders will get cancelled. So basically, odd orders of dispersion don't play any role. Even orders of dispersion are basically what determine the phase matching, and the most important term is the first, which is the first even order term, which is the beta 2, which is called GBD. Because basically the higher order terms are much smaller than the previous terms, right? So beta 1 is much smaller than beta p, beta 2 is much smaller than beta 1. Okay, so again, so for phase matching, what did we want? We wanted delta beta to be equal to 2 gamma p, right? So that delta beta total was delta beta minus 2 gamma p, which we wanted to be 0. So we want this delta beta to be equal to 2 gamma p. Now 2 gamma p is a positive number, right? Because gamma is the nonlinearity, it's a positive number. Pump power is also a positive number, so this is some positive quantity. And delta beta from here is minus beta 2 times delta omega square. So delta omega square, of course, is again positive. So basically from here, what it means is that beta 2 has to be negative. Right? Because minus beta 2 times delta omega. So minus beta 2 has to be positive. So beta 2 or this GVD parameter has to be negative for me to phase match my Fourier mixing process. Okay. And so this beta 2 negative is called anomalous GVD. Because it's actually not the normal thing that you will get for any material. So beta 2 less than 0 is what we want, and this is called anomalous GVD. So this is what we want to phase match the Fourier mixing. But typically, if you pick up any material, in any wavelength range you look, most materials will give you beta 2 greater than 0, which is normal GVD. That's why it's called normal, because that's the norm. You pick up any material, look at any wavelength range, typically you will see. Right? So, so what does beta 2 less than 0, right? So beta 2 is d of d omega of 1 over Vg, and that we want less than 0, which means what? As I increase my frequency, 1 over Vg should go down, or equivalently, as I increase my frequency, Vg also increases. Right? So this means as omega increases, group velocity also increases. Or in other words, like higher frequencies or blue frequencies travel faster than the red or lower frequencies. Right? Whereas normal is the opposite. Red travels faster than blue. right? So typically, if you pick up any material, so as a function of frequency, if you see the refractive index, it will look something like this. Right? With frequency, the refractive index goes up. And this beta is basically something like, so the propagation constant is k times n, right? And then you take the double derivative of this to get beta. Okay. So basically, typically the shape is something like this, and then you take the double derivative, you get a positive number for most material in most wavelength ranges. Okay, another way to see graphically why we need anomalous dispersion is, so if delta beta as a function of omega, right? So we saw this is minus beta 2 times delta omega square. So delta beta as a function of delta omega is quadratic. So if you have normal, beta 2 is positive, this is a negative parabola, right? Minus x square. So this is for beta 2 greater than 0. Whereas for anomalous dispersion, it's an upward parabola. Right? And for phase matching, I want, right, again, the condition was delta beta. I need to match with the nonlinear 2 gamma p. So 2 gamma p is a positive number. So if I indicate 2 gamma p here somewhere, then you can see if I have a downward parabola, there is no intersection with this 2 gamma p because it's always negative, right? But if it's an upward parabola, the parabola intersects this 2 gamma p at a particular delta omega, and those are the phase match frequency, right? So at this delta omega, delta beta becomes equal to 2 gamma p. So these two frequencies, so this signal and idler, will be exactly phase matched, and you get exponential gain for those frequencies, right? Whereas if you have normal dispersion, then there is no frequency for which you can match. Okay, so basically the task is how to get anomalous dispersion, right? So in the frequency, again, in this frequency axis, if I look at the gain, so for typically for any amplifier, you have like a plot of gain versus frequency, right? So, and I can see what is my bandwidth of the gain, etc. So we can try to do a similar thing here. So this is going into that node. Okay, so again the axis is delta omega, so detuning from the pump. So delta omega equal to 0 is the pump frequency here. And I want to look at the gain, the signal gain or the conversion efficiency. So close to 0 here. Basically delta beta is also 0. Okay, so let's look at first intersection point here. So So these are the frequencies which are exactly phase matched. So these correspond to our third condition that we were looking at, perfect phase matching, right? Delta beta total equal to 0. So we get exponential gain. Okay, so the gain is maximum for these frequencies. So if you plot the gain, it peaks somewhere for these frequencies. Okay, and the gain value here is exponential of gamma p, or goes as exponential some factor. Actually goes as e to the we got e to the gamma pl squared, right? So something like that. Sorry, e to the gamma pl by 2. So anyway, so that's the goes exponentially with the pump power. And now if I go, let's say, further away, my delta beta now further increases, right? And now it's much larger than 2 gamma p. So like, as I go to further detunings, my delta beta becomes larger. So I go to the large phase mismatch limit, right? The second limit that you consider. So this gain starts falling and you get these oscillations. So in this region, it's going like that sinc squared function. So you get these lobes of the sinc function. Okay, and then there is some minima in between here. Similarly on the other side. Okay, and this point just close to the pump frequencies, it again goes as gamma pl squared, which was our first limit. Okay. So typically, if you take a four-way mixing based OPA and you measure the gain as a function of frequency, so about the pump frequency, you'll get this sort of shape. Okay, so how far these lobes are apart depends again also on the pump power, right? So this is the point at which the delta beta becomes equal to 2 gamma p. So as I increase pump power, typically what happens is this lobe shifts out further. Also the peak gain goes up because power is going up, and it also shifts out further and it becomes wider. Okay, so the bandwidth, the gain, the bandwidth, everything scales with pump power. And we can estimate what this gain bandwidth is here, right? Basically, the width of this lobe is when basically so at this point delta beta has become equal to 2 gamma p. So right, minus 2 delta omega square is 2 gamma p. So this retuning delta omega, let's say bandwidth or something, is given by square root of right. So the bandwidth again scales with the pump power, and it's inversely proportional to the GVD. Right. So of course we want negative GVD, so minus beta 2 is a positive number. So you can see the bandwidth is larger if beta 2 is smaller. Right. So what does beta 2 smaller mean? If beta 2 is smaller, this parabola is shallower, basically, right? This coefficient is smaller, so it intersects at a further point. Okay. So you want beta 2 to be negative, but you want the value to be small if you want a large gain bandwidth. So basically, you just want it just a little bit smaller than 0. So you want near 0 dispersion, but slightly anomalous. Okay, so for wide bandwidth, want a small value of anomalous dispersion, anomalous GV. Okay, so if let's say beta 2 is too, the magnitude of beta 2 is too large, so it's negative, but the absolute value is very large, then the parabola will look like this, right? And basically, you see that you get phase matching very close to the pump and quickly become very phase mismatch. So this will start looking like this sync function already as soon as you go over from the pump frequency. For large, so this is for large negative beta 2. Okay, so the ideal case you want is negative beta 2, but just slightly negative, right? Not too much. That will give you a very wide bandwidth. So typically, people have demonstrated bandwidths of hundreds of nanometers. So let's say the pump is at 1550 nanometer. Okay, so people have shown this Fourier mixing based amplifiers for hundreds of nanometers on other side. So like this is going from, I don't know, like 1250. This is up to like 1900 or something. Okay, so using fibers and silicon waveguides, etc., you can adjust the parameters such that you can get very wide bandwidth. Okay, so as I said, you want anomalous GVD, which is actually not the norm, right? Typically, what you will have is normal GVD. So basically, like many things or many discoveries, there are some quirks of nature which help you at certain points. So basically, this whole optical telecom revolution happened with a lot of accidents that nature gave us. And one of them, for example, is, so if you take silica glass, which is what we use to make optical fibers, turns out the material has anomalous dispersion for wavelengths longer than 1.3 micron. Okay, so if you plot beta 2 for glass versus wavelength, you get something like this, and it crosses 0 at 1.3 micron. Okay, and you know that for telecommunications we typically use these wavelengths, right? So more than 1.3, 1.55, up to let's say 1.6 or something. So in the range of the telecom wavelengths, turns out that glass has anomalous dispersion, which was actually very strange. As I said, most materials have normal dispersion in most wavelength ranges. But this was a pleasant accident that nature gave us. And because of this, like a lot of telecommunications, the optical communication research was happening in these wavelengths, right? So the first OPAs, etc., were done in optical fibers at these wavelengths because automatically they could achieve anomalous dispersion. Have to do any special thing because glass itself had anomalous dispersion. Okay, so to give you some idea of values, so at one point we have brought in the center here. So beta 2 typically is measured. So I said the units are second square per meter. So typically it's measured as picosecond square per kilometer because in those units the numbers are nice. Otherwise you get 10 to the minus 24 or something. Right? So and it also, like in the optical communications context, this sort of tells you how much the pulse will spread after, like if you have a pulse of a certain duration, let's say some picoseconds, then after propagating some x kilometers, how much the pulse will spread. That's why it's also measured in these units. Right, so as I said, here it crosses 0 at 1.3. Right, so initially people tried to build optical communication networks operating at 1.3 micron because the dispersion is 0. So there won't be any pulse spreading, right? But it was observed that the loss was still too high if you wanted to propagate hundreds of thousands of kilometers. So that's why people moved to 1.55, where the loss of the fiber was even lower, which enabled you to go to longer distances. Right, so the standard telecom fiber, for example, at 1.55, so this value is about minus 10 or minus 20 picosecond square per kilometer. Okay, so this is standard. The standard optical fiber, so-called SMF fiber, single mode fiber, which is used for basically all the internet communications. The fiber networks laid down all over the world mostly use that fiber. Then you can get special types of fibers where you dope it with different elements to adjust the refractive index, or you change the shape of the core, etc. And you can shift this dispersion. Okay, so there's a dispersion shifted fiber, which basically has a shifted dispersion profile. This DSF, dispersion shifted fiber. Right, so with this, you can get near zero dispersion at the low loss wavelength of 1.55. Right, so that's basically the best you can do. You have zero dispersion and the lowest loss, so you can propagate the furthest distance. Right, so for this, you can get the dispersion down to as low as like 1.1 to 1 picoseconds per kilometer. Okay, so if you want to do this forward mixing process, let's say I have my pump wavelength at 1.55, then if I use a dispersion shifted fiber, my bandwidth will be like more than an order of magnitude larger than what if I just use the standard fiber, because my dispersion is much lower. Right? Next one. Okay, so for glass, yeah, it turns out you were just helped by nature. But for other materials, it's not so. Like for example, nowadays people make on-chip waveguides, right? And typically, let's say, if you use silicon, which is one of the most popular materials for on-chip photonics, like electronics also. So silicon, let's say in this infrared wavelength range, has normal dispersion, which means beta 2 will be always positive here somewhere. Just the material, if you take the material refractive index of silicon, it will always show normal GBT. But there was this whole push of doing nonlinear photonics and a lot of this telecom stuff, shifting from long fibers into small on-chip devices using silicon. Right. So then, how do you do that? So here, what is done is that the waveguides can be made very small. Okay, so these dimensions like the width and height, because the refractive index of silicon is so large, so it's about 3.4, right? And typically, like this will sit on some substrate of glass, so that has refractive index 1.4. So the index contrast between the core and cladding is very large. So to compare, for example, a standard optical fiber, right? So that has a core and cladding. So there the delta n, the difference between the core and cladding is very small, like 10 to the minus 3, 10 to the minus 4. But here you can see delta n is actually 2, right? So what that enables you to do is make the waveguides of very, very small dimensions. So this height and width can be much smaller than the wavelength. So for silicon waveguides, you can get down to dimensions. So this H and W can be like 200 nanometers. So 200 to 600 nanometers in that range. For wavelengths of, let's say, 1.5 micron. Right? So these are very, very small waveguides, highly confining. And for these types of waveguides, basically the dispersion due to the waveguide, right? So there is something called waveguide dispersion. So I don't know, some of you might have done a course on fiber and integrated optics. So you solve for these modes, right? And basically, even if you assume that the core and cladding refractive index don't depend on wavelength, right? So they're constant. Even then, you will see that for a particular mode, as you change frequency or wavelength, the n effective or the beta will change, right? So this beta is right. So this n effective is a function of frequency, even if the core and cladding have the same. Let's say the core and cladding refractive index you assume to be constant and don't depend on frequency. Okay, and that just comes because as you change frequency, the mode profiles will change slightly, right? So the n effective that the mode sees will change. So that is called waveguide dispersion. Okay, as opposed to the material case, so this is called material dispersion, which comes from the n versus the material. That's called material dispersion.
So the
Professor,
Video. No? Yeah. So the dispersion that you get just from the material refractive index, that's called material dispersion. And for optical fibers, basically the dispersion is mostly the material dispersion, right? Because these dimensions, so the core, if you look at the core diameter, so that's for single mode fiber, that's about 10 micron, which is much larger than the wavelength, right? Which is 1.5 micron. So the waveguide dispersion is very small. Mostly the dispersion is due to the material itself. But when you go to these very small dimension waveguides, this waveguide dispersion contribution becomes very strong, okay? And it can actually overcome the material dispersion. So in things like silicon nano waveguides, that's what is used. Just by using the dimensions of the waveguide, you force the waveguide dispersion to be much stronger than the material dispersion, and you can get a net anomalous dispersion, even though material dispersion is normal. Okay. So, for example, I've posted a paper on Moodle where they do this parametric amplification using silicon nano waveguides, and then they show that how by selecting the dimensions of the waveguide, they can do this. They can force the waveguide dispersion to go into anomalous region. Right, so yeah, that's. So basically, what I'm saying is the total GVD, you can sort of write as a sum of the material GVD plus the waveguide GVD, right? And so for silicon, if this is less than 0, you can make this thing, this is greater than 0. You can make this less than 0 and sufficiently negative that the whole thing becomes anomalous. Okay, so this phenomenon or this feature is also sometimes called dispersion engineering. So you're engineering the dispersion of the medium by selecting the dimensions, etc. So we only considered the dispersion terms up to the second order, right? But you could also include higher order dispersion terms. Let's say, for example, if you're working here, right, close to the 0 dispersion point, then you can imagine that the higher order dispersion terms will start contributing. So the next higher order term that will come is the fourth order, right? Because the odd order terms, as we saw, get cancelled. So, for example, if you include up to higher order, then the next higher order term, so we saw first term will be the GVD term. If you keep up to fourth order, the next term will be beta 4, so the fourth order dispersion. And that will scale as delta omega to the fourth power. Okay, so now like you can see what the shape of delta omega or delta beta will be as a function of the detuning delta omega. So if we just had this term, then we know it's a parabola. But now, if we had this fourth order term also, then if beta 4 and beta 2 are the same sign, then it will just add on to the parabola, right? It will just become a steeper size. But the interesting case arises when beta 4 and beta 2 are opposite signs, right? So let's say beta 2 was negative, but beta 4 was positive. So beta 2 negative means this is an upward parabola. But as you go out to further and further delta omega, this term starts contributing, and that contributes to opposite sign. So eventually, this will start dropping again. Okay. And now, basically, if I want to look at the phase match frequency, so I look at where it crosses 2 gamma p. right? So there'll be an intersection close by, which is basically just coming from the GVD. But there'll be another intersection far away. Okay, so this will be another set of frequencies. So omega I2, let's say, and omega S2. This will be omega S1. Right, so you'll get another gain feature which is very far away from the pump. Right, so this can help you.
Professor B, can you please switch on the video?
Yeah, so right, this can help you extend the phase match frequencies to very far away from the pump. Right, so by having beta 4 and beta 2 opposite signs, you can get a second intersection. So in the gain, you'll have one lobe here, but then another lobe which is much further away from the pump. So let's say you want to amplify certain frequencies or wavelengths which are farther away from the pump, then you can phase match it like this. And what it can also help you do is, let's say if you had normal dispersion, then we know that for normal dispersion, typically we can't get phase matching, right? So if we take normal dispersion, then we know that the parabola goes down and 2 gamma p is here. So there is no intersection, right? So we can't get phase matching. But now if we include the higher order term, let's say beta 4 was negative. So we had normal GVD, but beta 4 was negative. Then eventually this will start turning up. Okay, and then you'll get an intersection which is further away. Okay, so you'll actually get phase matching for some frequencies which are very far away from the pump. Right, so higher order dispersion can help you phase match even in a normal dispersion medium. Right, basically that's what it's saying. So yeah, tricks like these are also sometimes used. Okay, I just want to make a note about this GVD. So, because if you read papers or books, you might see some different notation. So, this beta 2 is what is called group velocity dispersion, right? And its units are second square per meter, or typically like picosecond square per kilometer. But sometimes this particular parameter is denoted by a slightly different quantity. Especially sort of in literature related to optical communications, etc. So they define this quantity capital D. Okay, so this is called the dispersion parameter. Okay, and it's defined as the derivative of the beta 1 with wavelength. So beta 2 is d beta 1 by d omega, right? Where beta 1 is d beta by d omega, or 1 over bg. So this d is defined as the derivative of beta 1 with wavelength. Okay. So this has units of picosecond per nanometer per kilometer. Okay, again, this is coming from optical communications, which says that if I have some optical pulse of certain bandwidth, which is measured in nanometers. So it has some spread of wavelengths of some nanometers, and then it travels through some fiber of certain kilometers length. Then the spreading that the pulse will get will be d times or d picoseconds times the bandwidth in nanometer times the length in kilometer. Okay, so yeah, in other words, this is basically how much would a pulse of bandwidth delta lambda equal to 1 nanometer broaden after propagating 1 kilometer. Right, and this broadening is measured in picoseconds. Okay, so of course D is related to beta 2. They are not independent, right? One is different derivative with frequency and one is with wavelength. So you can check that the relation between D and beta 2 is just this. Okay, so they are just related by constant which depends on the wavelength of operation. Okay. So this was beta 2 was in units of second square per meter. D you can check will be in units of second per meter square. Right, so that's why, so this picosecond square per kilometer is second square per meter. So D is measured in second per meter, which is second per meter square. Okay, so basically the thing to note here is the sign is opposite. Okay, this is just coming from the relation between wavelength and frequency. So frequency is related to wavelength like this, right? So when you take d omega and d lambda, you get a minus sign because it's coming in the denominator. So that's why it's minus. And that means that basically d greater than 0 is beta 2 less than 0 is anomalous. Anomalous DBT, and d less than 0 is normal. So yeah, in some places you might see this d and they say, okay, d greater than 0 means anomalous. But when you talk about beta 2, you'll say, oh, when beta 2 is less than 0, then it's anomalous. So just wanted to point that out. So it's just notation. In terms of the refractive index, you can see it depends on this. If you write this, so beta you write as omega over c times n effective, then this is the second derivative of n. So it depends on the second derivative of n. Okay. So, any questions? Yes, most of the people have left already. Yeah.
So how does the dimension of the so how does the difference between the diffractive index of the core and the cladding determine the dimension of the optical fiber?
Yeah. So this is a fundamental fact, right? So the how much you can confine a wave depends on. So you can think of it like a potential well, right? So the steeper this potential is, the sharper you can confine the wave. Right? So this is the core and cladding. So if the difference is very small, then even if I start reducing the size of the core, the wave will still be spread out. So it doesn't really help. But whereas the contrast is large, I can squeeze the wave to the core dimensions more. So yeah, that just comes from the solution of like the Helmholtz equation, or equivalently, this is the same as, for example, the solution of the Schrodinger equation, 1D Schrodinger equation in a potential well, right? If the well depth is more, then the wave is more confined. Similarly, if the refractive index contrast is more, then the electric field is confined more into the core. So,
Okay.
any other questions? So another way of saying that is, so remember we have this parameter A effective, which was sort of the integral of this mode function, right? And so that comes in the denominator of this factor gamma. So if that is small, then I can get a large nonlinearity. And so again, with these high index contrast waveguides, where the difference in core and cladding is large, I can really make this small, which means my A effective can be really small. So basically, I'm confining the energy of the photon into a much smaller area, so the intensity goes up. So that's how you can boost these nonlinear interactions and their efficiency by going to these nano waveguides also.